This lecture is for ELEC 1510 Logic Design on Combinational Circuits corresponding to textbook sections 4.1 through 4.4. Combinational circuits are generally referred to as higher level circuit designs. This means that they are more complex than the circuit designs that we've been dealing with in the previous couple of chapters. Generally, they're going to be multiple input, multiple output circuits. You're going to be optimizing multiple circuits at once, and these combinational circuits are often designed using subcircuits. In this lecture, we're not going to be talking about subcircuits, but in the upcoming lectures, we will be talking about subcircuit elements like encoders, decoders, and multiplexers that you can use to simplify the design of very complex combinational circuits. Combinational circuits are defined by the fact that they don't have feedback paths or memory elements. This means that the outputs in the combinational circuits only depend on the current state of the inputs. This differentiates combinational circuits from sequential circuits, which we will cover later in the class. Those have memory elements and feedback paths. The first topic that we're going to cover is combinational circuit analysis. We have a combinational circuit diagram on the left side of the screen here, and this combinational circuit has inputs A, B, C, D, and outputs F1 and F2. We want to write out a truth table that gives the behavior of outputs F1 and F2 for all possible input states of A, B, C, and D, but that's pretty tricky to do without first listing the behavior of subcircuit states within the combinational circuit, T1, T2, T3, and T4. So when we write our truth table, we're going to have all possible sets of inputs for A, B, C, and D. So that ranges from 0, 0, 0, 0 all the way to 1, 1, 1, 1. And first we're going to write 4 rows for T1, T2, T3, and T4 in the truth table. So let's first write out the logical expressions for T1 and T2. The T1 subcircuit output is going to be equal to B prime times C. Because B first enters an inverter and then the AND gate, C just enters the AND gate, and T1 is defined as the output of that AND gate. The output T2 is defined by the logical expression A prime B. So given that, we can look at, for T1, the lines B and C, and T1 is going to be a 1 whenever B is 0 and C is 1. For T2, we can look at the lines A and B and see that T2 is going to be a 1 whenever A is a 0 and B is a 1. So then we can fill in those lines in the truth table. Now we want to define logical functions for outputs T3 and T4. T3 is the output of an OR gate. The input to that OR gate is A as well as T1. For T4, the output comes from an exclusive OR gate where the two inputs are T2 and, XOR D. So T3 is going to be a 1 whenever either A or T1 is a 1. T4 is going to be a 1 whenever T2 or D is a 1, but not both of them are a 1. So then we can fill in the truth table columns for those two lines. Now, finally, we can determine logical expressions for F1 and F2. F1 is the output of an OR gate whose inputs are T3 and T4. So F1 is going to be a 1 whenever either T3 or T4 is a 1. F2 is the output of an OR gate whose inputs are T2 and D prime. So F2 will be a 1 whenever either T2 is a 1 or D is a 0. And so now we can fill in the outputs for those two columns as well. And now we have our outputs, F1 and F2, as a function of the inputs, and we define some sub-circuits along the way. So that's combinational circuit analysis, where we're given a circuit diagram and we determine the behavior of the circuit using a truth table. Next, let's talk about combinational circuit design. And so a very simple combinational circuit that we can design is a 3-bit gray code converter. The truth table for a 3-bit gray code converter looks like this. Gray code is a type of code that is sequential in the changing of bits, meaning that you only ever change one bit at a time, and it's used primarily in a field called analog to digital conversion. And it just results basically in fewer errors during analog to digital conversion, which you'll probably learn about in a different class. So it's a very handy code to use because it only flips one bit at a time. For example, let's look at binary. The binary number 1 in 3 bits is 001. The binary number 2 is 010, meaning that the second bit and the first bit both changed values. In gray code, you count up through codes without changing more than one value at a time. So 1 is 001 and 2 is 011, meaning that only one bit changed states. In the next conversion, the only bit that changes state is this bit, then this bit, then this bit, then this bit, then this bit. Okay, so gray code is useful for certain applications, and we want to design a converter that receives a 3-bit binary number and outputs the 3-bit gray code for that number. So this is basically just optimizing 3 different functions, x, y, and z, separately. The function for x, as you can see, is very simple. We don't even need a k-map to optimize this one. X is simply going to be equal to a, and we can see that just by inspection. For the function y, we're going to need a k-map. So this is for the function y, and we're going to write our k-map in terms of variables a, b, and c. And as you can see, minterms 0 and 1 are both 0. Minterms 2 and 3 are both 1. Minterms 4 and 5 are 1. And minterms 6 and 7 are 0. So now when we circle bubbles to optimize the function, we see that the function y is best optimized as a prime b or AB prime, which could also be written as A exclusive or B. For the function z, we also need a k-map. And I will fill in the minterms here, 0, 1, 1, 0, 0, 1, 1, 0. And circling bubbles, we see that z is going to be equal to b, c prime, or b prime c, which could also be written as B exclusive OR C. So now we want to draw the combinational circuit for the 3-bit gray code converter. We have input variables A, B, and C, and outputs X, Y, and Z. The output X is simply equal to A, so we can just draw a wire connecting those two variables. Y is going to be equal to A exclusive OR B. So the XOR gate looks like this, and we will connect A and B. And Z is equal to exclusive OR of B and C. So we connect it like this. And our combinational circuit for the 3-bit gray code converter is complete. This is a pretty simple example. A lot of the upcoming examples for combinational circuit designs will be more complicated than this one. But in general, this is the design process. You have multiple outputs. Each one of them has its own K-map. You optimize the K-map for each variable, and then you just draw the circuit for each output as a combination of the input variables.